Okay, we're going to move into solving polynomial equations. And just like with quadratics, one of the strategies is factoring. Okay, so factoring is not going away. It's coming right back. We learn how to factor quadratics either by, of course, what do you always do? What do you always look for when you get ready to factor? The thing I preached over and over.
Greatest common factor.
Oh,
Good. Tanner? Good. Greatest common factor. So that doesn't change. You always look for a GCF first. Now, y'all have somewhere in your notes a graphic organizer I gave you that has everything that all the strategies for quadratics. You look for a GCF, then count the terms. If there's two terms, you want to see, is it a difference of squares? Okay? And just for review, you don't have to write this down. But if you have a difference of squares, a perfect square minus a perfect square, remember you just take the square root of each one and put a plus and a minus in between them. So if you had x squared minus 25, that would be x plus 5, x minus 5. You with me? All right. And then if there were three terms, then you had to determine product and sum or guess and test. Okay, and was there anything else? I think that's pretty much it, wasn't it? Okay. All right, so now we're going to be dealing with polynomials that may have higher degrees than just two. It may not be quadratic. It could be a cubic or have a fourth degree. Okay, so just like the difference of squares, there's two other factoring techniques that you just memorize the pattern. Okay, and that's for sum of cubes and difference of cubes. So if you count your terms and you have two terms, after you factored out a GCF, of course, then if it's not a difference of squares, if you see cubes in it, then it may be a sum or a difference of cubes, which is a perfect cube plus a perfect cube or perfect cube minus a perfect cube. Now for squares, the only thing that worked was difference of squares. There was no sum of squares strategy, okay? But here you have either sum or difference. And then what you do, here's your pattern right here. If it's a sum of cubes, then you take the cube root of each one of them. The first factor will have the cube root with the plus in between them. The second factor will be a trinomial factor, where you'll square this first number, then multiply these two together, and then square the second number. Okay? If it's a difference of cubes, it's the same idea. There's just sign differences. There'll be a negative here and a plus here, but the same idea. Okay? And then if a polynomial cannot be factored at all, it's called prime. We'll talk about that too. Try to get the right folder going here. All right, so example 1, we want to factor these, okay? We're not solving yet. We're just factoring. Remember, solving is going a step further and setting it equal to 0, but we're not going to do that. We're going to get used to factoring first. So example 1A. I've got to kind of keep my eye on that screen too. All right. (27) m cubed minus 64. Now, before we go any further, I forgot to do something, okay? If we're going to be looking for perfect cubes, perfect cube minus perfect cube, then we need to be familiar with our cubes, right? Just like our squares, we have 4, 9, 16, 25, 36. Well, those are not the same numbers we're going to be looking for with cubes. We need to know our perfect cubes. So we're going to write, and somebody's got a calculator handy, you're going to have to help me out at some point. We're going to write our perfect cubes from 1 cube through 10 cube. We're just going to write it out here to the side. Okay, y'all ready? You probably want to write this down. So 1 cubed is 1 times 1 times 1, which is 1. Which 1 is a perfect square and a perfect cube. All right, 2 cubed is 2 times 2 times 2.
No.
8. 3 cubed, 9 times 9 times 9.
27.
4 cubed, 4 times 4 times 4.
16 times 4. Hold on, I got it. 54?
Close.
64.
5 cubed, 5 times 5 times 5. 5 times 5 is 25 times 5. That's 5 quarters. What's 5 quarters? Yeah. 6 cubed, 6 times 6 times 6. That would be 36 times 6. 216. And I don't have these completely memorized, but I do recognize them. So if you tell it to me wrong, I'll know. 7 cubed, 7 times 7 times 7. So 49 times 7. Somebody has a calculator handy. Y'all going to need help. What? 300 what? 343. Yes, that's right. 8 cubed, 8 times 8 times 8. That would be 64 times 8. 512. 9 cubed, 9 times 9 times 9. That would be 81 times 9. 729. 10 cubed, 10 times 10 times 10. We should be able to get that one.
200. I'm listening to you behind up that stuff.
I'm so tired right now. Like,
Did you say 200?
I did.
Okay, so these are the numbers we're going to be looking for. Now notice 64 was also a perfect square. It was 8 times 8. But it's also a perfect cube. But the cube root of 64 is 4. The square root of 64 is 8. So you have to keep that straight. Okay? All right, so now let's go back to our problem. What's the first thing we always want to check for? A GCF. Do we have a GCF? What number can both of these be divided by?
Oh,
The largest.
4.
No, 27 can't be divided by 4.
9.
64 can't be divided by 9. No. So I'll just go ahead and tell you, there is no GCF other than 1. Okay? So now, next thing, count your terms. How many terms do we have? 2. So normally, up until today, you've always looked for a difference of squares, which of course this isn't. I see a cube. Okay, but now we have this new strategy looking for sum of cubes or difference of cubes. So it's a difference. Now, is 27 a perfect cube? Yes, it's on our list over here. Is m cubed a perfect cube? Well, yeah, m cubed would be a perfect cube. All right, is 64 a perfect cube? Yes, it's on our list over here too. So what you're going to do is you're going to use the little pattern. Now up here, if it's a difference, we're going to have a binomial factor that has a subtraction sign here. And we're going to have a trinomial factor that has 2 plus signs, 2 addition signs. So now you don't have to worry about signs. So just don't even worry about that negative that's there now. We've already taken care of the signs. All we want to do now is take the cube root. So what's the cube root of 27m cubed? 3. What about the m cubed? M. The cubic root of m cubed is m. What's the cube root of 64? So there's your first factor, 3m minus 4. Okay, now look at these to get this. So if you go back up here, our 3m is our a. So we want to square the 3m. What's 3m squared? We want to square 3m. No, square
Oh.
it.
So would it be m squared?
Well, the m would be, but what about the 3? 9. So it'd be 9m squared. Okay, then you just want to multiply the two together. 3m times 4. 3m times 4, 12m. And then you want to square the b. So you want to square this term. 4 squared, 16.
Why would you put the sign with it?
Because the signs are already taken care of in this. That's why I said a while ago. Go ahead. That's why I go ahead and put the signs, and then you don't have to worry about them. Okay? All right. So now we have a quadratic here. So we could check that and see if it is factorable. We'd have to do guess and test. But I can go ahead and tell you right now it's not going to be factorable. Okay? If we were to solve, we would have to use quadratic formula. So that's our answer. No, the sum and difference of cubes is just like the difference of squares. It's just a pattern. Okay? There's nothing magical about it. All right, example 1b. 24x to the 5th plus 3x squared y cubed. Tanner, what's the first thing we want to check for?
GCF.
There you go. Good. Okay, do we have a GCF? You got to look at your numbers and your variables. Can we divide? Do 24 and 3 have a GCF? 3. Yeah, 3 will go into both 24 and 3. What about the variables?
I think you had to subtract those. So you put
I have an x squared and an x to the 5th, so I can factor out an x squared. But now I don't have a y in this first one, so no y's can be factored out. So I can factor out a 3x squared because we have an x squared in common. So basically, when you factor out, that means you're going to divide both of these by 3x squared. So what's 24x to the 5th over 3x squared? 8. And then you subtract your exponents. And then what's 3x squared y cubed over 3x squared? Just y cubed. Okay, so we factored out a GCF. So now, look at what you have in parentheses. How many terms? 2. So what are we looking for? Sum or difference of cubes. I don't even have to worry about squares because I don't see they're cubes, they're not squares. So I want to see it's a sum. So do we have a perfect cube plus a perfect cube? Is 8 a perfect cube? Is x cubed a perfect cube? Is y cubed a perfect cube? Yes. So we do have a sum of cubes here. So we're going to use this right here to factor that. So I'm just going to bring my 3x squared down because it's a factor. Now, if it's a sum, you're going to have a plus here in the first factor, then a negative and a plus in the second one. So we're going to have a plus here, then a negative and a plus. Now, I don't have to worry about my signs now, okay? The signs are taken care of, so just ignore the signs. I know that doesn't happen very often when you say ignore the signs, but since this is a pattern, we can. All right, so now we want the cube root of 8x cubed. 2x. And we want the cube root of y cubed. Why? Yes. Because what did we multiply together times itself 3 times? That's y. That's your cube root. All right, now we want to square the first one. So what's 2x squared? 4x squared. We want to multiply the two terms together, 2x times y,
So 2xy.
2xy. And then we want to square the last one, y squared. And this is not factorable. So these are our factors. Now, if we were going to solve, we would set each one of these equal to 0 and solve. But right now, we're just going to work on the factoring. We need to get that part down first. Okay, one more. And this one won't take long. X cubed minus 400. Let me ask somebody besides Tanner. Ryan, what do we look for first? Yeah, you did. I heard you. You said it real quick. I heard you, Ryan. Go ahead and say it, Ryan. A GCF. Do we have a GCF? No. Okay. So, how many terms? So, what am I looking for? We're looking for a difference of cubes. All right. Do we have a perfect cube minus a perfect cube? Very good. The first one's a perfect cube, but what about 400? So, this one is not factorable, which means that it is. Yep. Very good.
No,
She highlighted it actually.
Really good. I just forgot the difference.
Okay. Any questions about sum and difference of cubes?
No. She's recording. They don't care. You might want to record it at different class.
No, they're going to be quiet so I can finish my recording. Right,
I'm
Tanner?
about to rewrite these notes.
Right.
I'm going to make y'all listen to yourselves in a minute. Now, shh.
Can we do that, please?
All right.
That'd be very entertaining.
That would be funny.
Now, this is a summary over the things we've learned about factoring. No matter how many terms there are, you always want to look for a GCF, okay? If there's two factors, you want to see is there a difference of squares, a sum of cubes, or a difference of cubes. And look over here, they give you those patterns again. All right, if there's three terms, then you want to look for, actually, I just taught you this because just factoring trinomials using product and sum and guess and test will work for perfect square trinomials. So I didn't teach you two different ways, okay? So this is the product and sum, guess and test. All right, and this to me over here is kind of confusing. So, all right, now we're going to move into, well, what if you have 4 or more factors? Well, the first thing you do is look for GCF. But then once you've done that, there is another strategy. It's called grouping. Okay, so that's what we're going to look at now. So, example 2A, and my directions are to factor. So, example 2A, I have x cubed plus 5x squared minus 2x minus 10. So what's the first thing I want to look for, Kiana? A GCF. Do I have one?
Didn't you with the X though?
No, I can't factor out an x because I don't have an x down here at the 10. So is there a GCF? No. Okay. So what we're going to do now is, since there's how many terms? 4. We're going to try what's called grouping. And what we're going to do is we're going to group these two together, and we're going to group these two together. So I'm going to look at these two as if they were all by themselves right now. Do they have a GCF? What is it? X squared. So I'm going to factor out x squared. Then divide both of these by x squared. And what do you have left?
X plus 5.
X plus 5. Okay, now I'm going to go to these two.
-2.
Yes. And normally, if this one is negative, you want to go ahead and factor out the negative. So you're going to factor out a -2, and what do you have left?
X is
-5
oh, positive.
plus 5. You got to change the sign, because if you multiply it back together, -2 times x is -2x. -2 times 5 is -10. Okay, now we just factored the GCF out of this group and this group. Now we've got two terms again. We've got this and we've got this. And I see within those two terms now another GCF. What do these two terms have in common?
5.
What's that right there? X plus 5. So we can factor out the x plus 5. So that means we're going to divide both of these terms by x plus 5. So what do we have left over here?
X squared.
What do we have left over here? That makes our other factor, what was left over. Now, x plus 5, I know cannot be factored anymore. But what about x squared minus 2? How many terms does it have? 2, and I see a squared, so I need to check and see. Maybe it's a difference of squares. Is it? X squared is a perfect square, but what about 2? Is it a perfect square? No. So we're done. Okay, example 2b. A squared plus 3ay plus 2ay squared plus 6y cubed. Winner, what's the first thing I want to look for? A GCF. Do all four of those terms have something in common?
No.
No. So how many terms are there? I just said that, but 4. So what do we want to try? We want to try grouping. And normally, it'll work to group the first two together and the last two. Sometimes, if they want to give you a little more challenging problem, you may have to rearrange the terms somehow. But normally, that won't happen. And you just don't know until you factor and try it. Okay? So, what will factor out of this? A. And what do I have left?
A plus 3y.
Good. Okay, what can I factor out of this?
2y squared.
And what do I have left?
A plus 3.
Oh, A plus 3y. Imagine that. So in this term, what do I have in common?
A plus 3y.
A plus 3y, so factor it out. And then what do you have left?
A plus 2.
Now both of these variables are linear. They only have an exponent of 1, so I know I can't factor it anymore. But I see a squared over here. So always double check. There's two terms and make sure it's not a difference of squares. And of course it's not. It's not even a difference, much less a difference of squares. So we're done. Okay. Now I'm going to give you two practice problems that I want you to try right now. And we're going to check them about 5 minutes or so.
Listen to the video.
All right, now. All right, the first one is 5y to the 4th minus 320 yz cubed. And I put a little line through my z so you don't get it mixed up with the 2. And then number 2, 5x cubed minus 35x squared minus 7x plus 49. Okay. And I have figured out, well, I'm not going to worry about that. All right, I'm going to stop the video. I'll have to restart it in a minute. I'm ready to check them.